All right, I think that we can start. So welcome to the Warren seminar, and it's really my pleasure and honor to introduce Professor Balakumar Balachandran, and I think that's in short for Bala. And Professor Balachandran is the Minta Martin Professor in the Department of Mechanical Engineering. He's also the chair of the department. And just a few words about him. He started his life as a naval architect, getting a degree at IIT Madras, and then moved to the US. Then he got a degree in MS in aerospace engineering, and after that moved to a PhD in engineering mechanics, and as his advisor, Professor Naffey, who is very well known, people in perturbation, multi-scale methods. And a bit later on, went to the University of Maryland. Maryland, and where he's now has been professor since that time, since 1995. Professor Bala is a very prolific writer. He has written a lot of papers in a diverse field, but he's in the space of nonlinear phenomena, vibration, control. And the object of his studies varies from kind of aerospace and stability of stator and rotor, to also drilling mechanics. And that's one of the reasons why I invite him to come here, because he has written some excellent papers, very well-known papers on the stability of drill string. And actually one of his papers was instrumental for one of my PhD students who start to work, who continue the work that Bala started. So please join me to welcome here, and I really look forward to it.
Okay, good morning, everyone, and thank you. A big thank you to Emmanuel Detourné for this opportunity to be here today, and to all of you for being here on a cold morning, at least very cold for me. So, as Emmanuel mentioned, I'm right now in the Mechanical Engineering Department at the University of Maryland. I know Chuck Schwartz was here last fall. I'm one of 47 faculty in the department, which is 125, which will be 125 years old next year. I think I'm in the Mechanics and Materials Division, which is the curricular division to which I belong, in which, as Emmanuel pointed out, I teach courses in dynamics and vibrations and mechanics as well. Some of you might see some familiar names in the chart. Avi Barcohen used to be at Minnesota before Mechanical. He's now with us in Maryland. So in terms of my interests, I'm by and large interested with nonlinearities, as this particular chart illustrates the range all the way from small scales to carbon nanotubes, where one drives down the length scales. It's inevitable that one will have to deal with nonlinearities, to things in nature, in terms of flying vehicles and such, as well as hummingbee out here, where the wings deform in a nonlinear fashion, to schools of fish and how they deform themselves in nonlinear schools to move around, as well as to more civil engineering structures where vortex-induced vibrations, as well as other aspects of nonlinearities come into play. So in my prejudiced way of thinking, I do think nonlinearities occur in many different places. In today's talk, I'll be talking about drilling, which shares many similarities to milling, which is one of the first topics I got into when I got into Maryland. Back in '95, I started working with NIST, where we started looking at high-speed machining. And at that time, the interest was in how do you machine very hard materials with the long tools. The idea is one would take a big block of material and machine it all the way down to the part that you needed. So the question was, how do you find the right operational parameters in terms of tool speed, RPM, and such? I think it shares similarities to the drilling process as well. At another extreme, this is an aerospace structure in which the large wing shape, the helios, gives it geometric nonlinearities in the system that one has to reconcile with. In fact, this particular rendition had encountered an unfortunate incident in which a wind gust put into another limit cycle state. The large amplitude was pretty much broke the aircraft up when it was in flight. So nonlinearities can do dangerous things to you. The MEMS resonators at a different scale, again, the interesting phenomena in that particular regions as well. In terms of drilling and disc brakes, the friction that occurs between the pad and the disc out here that type of nonlinearity occur in drilling as well. So again, it's a very rich system in terms of phenomena that one could see. So nonlinear systems exhibit rich dynamics. A couple of things that one might expect to see in those type of systems. The response depends on the initial conditions. So unlike a linear system, depending on where you start from, that could determine where you end up with in terms of final steady state. In the drilling case, there are multiple steady states of what one could go into. Perturbations could take you some different places. At a fundamental level, the frequency of oscillation can also depend on the amplitude of motion, unlike in a linear system. And for a harmonic input, typically in a linear system, one would expect a harmonic output, whereas in a nonlinear case, you could have periodic, quasi-periodic, and aperiodic responses as well. And nonlinear resonances are another thing that's common. Bifurcations, we'll talk a little bit about that. All that means is a qualitative change in the dynamics. As you change a parameter in the system, how do we go from one state which has certain features to another state, just slightly different features. You'll see certain aspects of that in the talk today. And you could also have energy exchange among modes of oscillation. That's typically when you have large systems. So this, of course, we've been a little bit brave. We've been teaching a course on vibrations at the undergraduate level. We try to sneak in some of these ideas at that level as well, primarily through numerical work that students could pursue. Now, coming to the subject of the talk today, drill strings. I know we have experts in the field in the room, so sorry if I bore you with the details. With the drill string, here's a schematic of the system, one rendition of it where you have a hoisting system and a motor which turns, a turntable which in turn is connected to this long drill string which can run several kilometers below the ground. A part of the drill string is the drill collar at the end, which is probably several hundred meters, which puts a weight on the bit. Although this is called a string, typically when people think of strings, a string is in tension. Whereas in this particular case, due to the compressive load at the bottom, you also have a compressive load at one point below towards the lower section of it. So our interest is to see if we could develop reduced order models to explain phenomena that one might see in this type of system, as well as examine instabilities that might occur and how that depends upon operational parameters like the penetration speed as to how deep, how fast can you take it down, or the rotation speeds and such. And in particular, we are interested, given what I said before, milling, how does delay effect play a role in the dynamics, and what type of system instabilities might occur due to those delay effects. So the nonlinearities are many different ways that can come into play. One is contact. So if you envision this drill string being a borehole, like what you see out here, the contact between the bottom and the drill string, the drill bit, so that contact could be intermittent. You could have friction at that location. You could have it on the sides of the wall as well. Those in the model would give us nonlinear features. That again, partly is due to nonlinear friction forces. You could have coupling between vibration modes. The energy gets transferred from one vibration mode to another. Of course, given the length of these strings, you could have large deformations. So these are just a subset of the nonlinear effects that one could see. This is borrowed from Schlumberger's rendition of different type of motions that one could see, ranging from bit bounce, where basically the bit bounces off the floor. You'll see a little bit of that in what we see in the work today. Could also lateral vibrations, where it vibrates due to bending motions. Torsional motions, where the thing whirls in the stick slip, although it's just mentioned in that context, you could have stick slip both in the axial direction as well as torsional as well. And whirl motions is another one that you'll see in the talk today. So when we first started working on this project, I think we were brought into this by the National Drilling Company at Abu Dhabi. They were interested in finding out what type of drill mud pressure they should use to keep the drill bit in the middle of the bore well. And they also were interested in finding out how they could avoid failures like what you see out here. This is typically due to bending strains being excessive, and you have these cracks that develop in the drill string. And then you could also have torsional strains that lead to shear strains that lead to failures where you have the couplers. Those are the two main failures that they were interested in finding out how they happen. And part of our study was to figure out ways to explain, what could help them in terms of operational procedures they could undertake to avoid these type of undesirable situations that they encountered. Because typically when these things happen in operation, they cost them about several $1 million to stop and start to clean up the whole bore well and such. So we took an approach which you'll see multiple components as we go through the talk. So one aspect of that would be how might one use reduced order models to look at these dynamics. And what happens as the dimension of the system is changed? Does that change the dynamics that you see? Or are you able to capture the phenomena of interest? And third, would it also provide you some clues as to what effects are more important? So you'll see the word stick slip throughout the talk in different places. So all that means, if you've not heard of stick slip before, is a speed, relative speed between two surfaces in contact goes to 0, like you see in this case in the torsional direction, or the axial direction, up and down motions, where the bit, when it makes contact in the axial direction, the speed drops to 0. Now, if I go back to this rendition, so basically what you have is a borehole on the side, and then you have drill string shown in green, and then you have drill collar shown in yellow out here. At the bottom is where you have the cutter. And then we use terms, the torque on the bit and the weight on the bit, which are two important things that we worry about. And the control parameters in this case, at least from a dynamic standpoint, are two of them, two major parameters. One is this penetration speed, V naught, and the rotary table rotation speed, omega naught. So that you'll see in many different forms throughout the talk. The key points are how do I choose these parameters to avoid undesirable dynamics at this very end. So from a control standpoint, it's a very interesting problem because all your control is being done out here, whereas everything that you want to control is at the bottom out there. So it's non-collocated. So it brings up interesting issues in terms of how one might think about it. So at the cutter, if I were to take that out, you see two flutes of the cutter out here, and the rock out there. And I've shown you a symbol Z of t and Z of t minus tau. Z is a displacement in the vertical direction. And that's a time-delayed displacement. So pretty much anytime you cut something, if you don't cut something in the first pass, you have to cut that material in the second pass. That's where the time-delayed tau comes into play. That's a constant delay. This is your depth of cut, or the instantaneous depth of cut, as they call it. Phi of t is an angular variable. So again, this could vary right along the drill string. And what you see out here are results of a simulation where essentially if I take a time history of the angular speed of the bit, the base pretty much goes around, and then I have a phase where it sticks, and then when it comes out of the sticking phase, there's a big change in the RPM. So that's what you typically see out in the field as well. When you're stuck, you have a lot of stored up potential energy which is released, and you come out and start spinning at a much faster speed. And of course, for us, the delay effects play a huge role in determining the speed as well. And in this case, when you have a sticking phase in the angular motion, the same thing happens in the axial motions as well, although this is not necessary in all the cases that you will encounter. So part of the model of this, again, this goes back to work that Emmanuel had done many, many years ago. We followed his approach in terms of drill bit rock interaction. We took the weight on the bit and the torque, broke it up into two pieces. One is the cutting part, cutting component. Now there's a friction component. The same thing for the torque. If you were to break them up, the cutting, you could see there are functions, the ramp function until instantaneous depth of cut, and the step function in terms of the torque speed. And then you have another, there's likewise, you have the cutting parameters that come into play, and so forth in the different models. So again, this is where the nonlinearities come into play. The drive friction, the loss of contact, and those things come into play. And also the state-dependent delay, although I've not mentioned that as a source of nonlinearity, when you go through and examine that, one could also envision that as being a nonlinear term because it's an implicit function. So how does the state-dependent delay come into play? So pretty much a state-dependent delay for us is if I'm rotating something, if I start at a particular place, how much time does it take for me to come back to the same location? That is pretty much a delay. And that delay is an implicit function of the states of the system. So that's something that we need to find. So the drill bit rock interaction, I think before the seminar today, I had an interesting discussion with one of the former postdocs of Emmanuel. So I was talking to Ganesh about the drill bits. So these are some typical parameters that we'll be using in the study today. They're all particular to this PDC bit, the cutter. Again, the modeling goes back to Emmanuel's work, the early 90s. So in one of the models that you'll see, we pretty much take the drill string, which is a long continuous system, and do a spatial discretization. So that discretization leads to discrete elements in terms of inertia and stiffnesses that are grouped together at different locations along the length. And we break up your drill string or the drill pipe into a number of elements, and the drill collar into a number of elements as well. And then you have your drill bit right at the bottom. If you take all those different elements, you could write them out at least, if I don't worry about the delay, in terms of a finite dimensional system of equations. So if I choose 32 nodes, for example, altogether, so that will lead to about 64 states. And in the state space, if I include the velocities, speeds, this model would be with 128 first-order equations. Okay. Now, what makes this problem complicated and interesting is the right-hand side term, where the cutting force and the cutting torque out here. So the delay terms appear into play. And apart from that, through phi, I also have the state-dependent delays that come into play. So that pretty much is where all the dynamics, from a dynamic standpoint, that's where all the dynamics comes into play and makes it interesting. So when we went through that system, this is just to give you a snapshot of what happens. These are axial motions of the bit. You see that it oscillates, and if I were to pull them out in an expanded window, you see that the drill bit also has negative speeds. So pretty much it's telling me I'm losing contact and bouncing off the surface. It's bit bounce. I also have phases where the speed hits 0. That's the speed where it sticks. And likewise for the torsional motions, again, I have a sticking phase and a slipping phase. So all of this comes out of the model that we looked at. And the sticking and slipping, although we focused out here at the time histories at the very bottom, the drill bit, this can happen at many different locations as well in terms of the interplay. And there's also another interesting aspect, is the sticking that happens in the torsional motion does not imply that you'd have sticking in the axial motions as well. Okay? So these are all purely numerical studies where we take the delay equations, and then you numerically integrate them using an Euler-Maruyama scheme, and then you can obtain your governing. So another thing, when you have a model like this, one could look at also wave propagation. So if I take this system, and what you see in one of the cartoons is this one out here shows me how my system is discretized. I have 32 nodes. And roughly I have, this is about 1.3 kilometer long structure that we've taken. About 200 meters of that is a drill collar. And we have a particular non-dimensional RPM, which is about 200 RPM. And the penetration speed, again, is non-dimensional. And we look at the related displacements in axial and torsional directions to obtain the strain plots. And what you see is how these waves propagate. A couple of observations stand out. The shear strain is an order of magnitude higher than the normal strain or the axial strain. In addition, there are also a couple of locations, I believe around the 26 or 22, you hit some node points in the axial strain. And about 15, you hit an anti node in the system. So this type of work, what it allows you to do is with this model that one has, which is a little counter to other models before, wherein with one looks at the lesser number of states. This allows you to look at the wave propagation through the system itself and also provide you an idea about the relative magnitudes of the strains. Now, so a key thing for us is also stability of motions. How do I look at stability? So earlier I talked about spatial discretization. So we went for a system for this 1.3 kilometer long system, which we went through and ended up with 128 states of the system. Now for the delay, we take that delay and also discretize that using a semi-discretization method. So in our particular case, we discretize the system with about 40 states in the period of the system. And so from our governing ordinary differential equations, you can end up with a map. So essentially has this dimension where n is 4n is 128 out here, and 2m is 80 in our case. It's a high-dimensional map of the system, which one could use to find the stability of the system. So what does that mean? If I take this map and look at solutions of it, then I can go back and infer solutions of this system out here, which is linearized. So in the linearization, I kind of went through it, glossed over it, but the state-dependent delay was approximate as a constant delay in our particular case. And then, so the objective of this analysis is to find out regions in the parameter space, be it the axial speed or a cutting coefficient, or the parameter space of the axial speed and the spindle RPM, to look at regions where you have stable motions. And if you go through that analysis, this is sometimes called as flow-K theory or flow-K analysis. From the map, if all the eigenvalues stay within the unit circle in the complex plane, then you have stability. So if I take one representative plot in the plane of your penetration speed and your rotation speed, the green region is where you're stable. So pretty much if I had a drilling that was taking place at a certain speed and a certain RPM, what I would expect to see at the drill bit would be at the same speed and same RPM. Whereas if I end up at somewhere on this boundary, or on this boundary, then I would start moving as I cross this boundary, that particular motion would lose stability, and I would see other things that will come into play. Now, another thing of interest for us is the nature of these boundaries. Would I go from a stable to an unstable region in a smooth way? So if I'm operating the system, if I change the speed, if I'm increasing the speed, if I go through this boundary to this region, do I transition a gradual way, or is there a big jump that happens? So that's, again, something of interest for us to find out. And be it said, with what we have right now, with the linearization, it doesn't carry that information, but I'll just talk about that in a bit. Another interesting thing that came out of this analysis is that if I increase the number of dimensions of the system, as I go further and further, the region of stability kind of shrinks. So that's kind of interesting for us, at least. So what that means is for any given operating parameter space, if I need a true representation of the system, that's then the sliver in which you have stable motions or the periodic motions at what you put in is quite limited. So as you go further and further out, it's very likely that you'll end up with a stick-slip oscillation, which is unstable. Now, in order to get a better handle on how this thing happens, so in this, what I have so far, we approximated the delay, and we have also made some assumptions, and everything is numerical. The question is, could we get some analytical insights into what happens in this case? So for that, to do the analysis, we went back to a model that Emmanuel Detourné worked on fairly recent, almost 10 years ago. So we went back to that model, where you take the whole drill string system, have a representative model, pretty much where instead of looking at the 128 states that I talked about before, we have 4 states and the same cutting forces and the same friction components. So this system has an equilibrium solution. So pretty much what that means is if I have an input penetration speed and an input RPM, the output of the drill bit would be this particular penetration displacement and that particular RPM, angular displacement. So the question is, how do I find the stability? And this stability, how is that influenced by the state-dependent delay? So I'll just walk you through these slides. So pretty much we went through this process where we take the full nonlinear equations, put them in non-dimensional form. In tau hat, in this rendition, this is my state-dependent delay of interest. N is the number of cutter fluids, and psi depends on my cutting coefficients. V naught is my penetration speed. Omega naught is my spindle RPM. And then you can go through and put them in state space form. Essentially, these are my 4 states of interest, the axial displacement, the axial speed, rotational displacement, or the angular displacement, and the angular speed. And then you end up with this nonlinear vector field. Then this is your state-dependent delay. Okay, so now the question is, how do I find the stability of the equilibrium point of the system? So the linearization is a little, one has to be careful in these problems. As with the state-dependent delay, one cannot take a derivative of the solution itself with respect to the delay. So one has to come up with a quasi-linearization, which pretty much the same local properties as your original system. And to do that, one has this additional term, which is common in these type of problems. So once you construct that particular system, so this is a Freck derivative that one has to construct in this case, you end up with this particular linearization. So what is striking in the system is that if I were to focus on all the blue terms, those are the terms that appear with the state because of the state-dependent delay. So if I went back and took my constant delay model, I pretty much would lose these effects, pretty much all of which depend upon the penetration speed. So these terms out here would drop out of the picture. So that's a salient difference with the previous work or the previous approach and what we have out here. So that's very critical. So one could go through the same machinery that one would use in this case to come up with the characteristic equation, no difference here. And then you could come up with the stability boundaries for the system. This is for the state-dependent delay. The penetration speed and the RPM, pretty much these would tell me at what regions I would be stable. And then I can construct my boundaries. I can do the same with the constant delay. So if I do that, I end up with this picture. Well, pretty much I'm going back to the same rendition that you had before. The operational RPM on the x-axis and the penetration speed on the y-axis. And you see that I have this upper boundary, which is a steep boundary, and then the other, right, the top boundaries, which kind of take the shape, which the damping influences, and as you go down. It turns out that the constant delay influences this boundary, as the state-dependent delay influences these boundaries out here. Okay. So one clue that we get from out here is the stability region that I have. Of course, this should not come as a surprise with damping of axial as well as torsional motions. If I can damp them more, the stability boundaries, the stability region is enhanced. There's also another benefit of doing that, which you'll see in a bit. If I go further now and examine what happens at these locations, before doing that, if I were to look at the cutting parameter or cutting coefficient and the RPM, you'd see that this boundary that we got for the constant delay case overlaps with the state-dependent delay case, whereas other boundaries change with the state-dependent delay, indicating my stable region reduces in size in this space when I just went to the constant delay model. All right, so the nonlinear effects. So the nonlinear equations, so the nonlinear is pretty much is the state-dependent delay. That's where it produces the nonlinear terms for us. So this is what in dynamics we call as half bifurcation. Pretty much all that means is if I were to take a parameter of interest, for us in our case the penetration speed or the spindle RPM, and plot the amplitude of motion, be it an axial displacement or a torsional displacement, As you change your parameter, if I were to follow this graph, everything is good. Pretty much the system response at your penetration speed and your input RPM, but after a certain point, it encounters instability and goes off along the upper branch. However, there's a smooth transition. Okay? So this particular thing in different fields is also called as flutter, the same thing. This, on the other hand, is a little different. What you see is as I walk down this path, after I hit the unstable point or the bifurcation point, I jump up to an upper branch and then follow along this curve. So what is interesting about this is if I'm operating the drilling rig, for example, and if I encounter a subcritical instability, my natural reaction would be to reduce my penetration speed or a parameter of interest. So if you do that, you would come down along this path, but you'll have to go further down, way beyond where we initially had before you come back to a stable state. So subcritical instabilities are in general fairly dangerous instabilities to have. And so these are things we try to avoid. So the question for us is, in our particular case, what parameter, what dials could we turn to control this particular instability? To do that, we went back to our governing nonlinear equations, and then to do the analysis, we had to put it in explicit form. We did an approximation where we kept the first two terms in the approximation. And if you do that, you can predict your instability. So what turns out is you can clearly see that with the increase in damping, it starts behaving more like the supercritical case that I would like to have. With lower levels of damping, I could end up with subcritical bifurcations as well. So which is, again, a clue for us that this torsional damping or axial damping could help us avoid this undesirable dynamics as well. Whirling motions are of interest as well. This is a different aspect, but there's no cutting action. But what I want to highlight is you could have multiple solutions, be it either when the system whirls the same direction as your drive input without making contact, they bore well, or it rotates with making contact, or another case where it kind of spins in a backward direction. So this is the case which you would like to avoid, because when you're backward whirling, you could rotate at much higher speeds than your input speed itself. So this is a lab scale rig that we worked with. Again, so if you were comparing it to what you saw before, this could be a section between two stabilizers in your drill string. A key aspect is the first bending and the first torsional frequencies are on the same order. If you do that, so in the forward whirling case, you'll see that, excuse me. You see that it rotates at the same direction, but the speeds are about what you put into the system. But the backward whirling, you end up with a much higher RPM than what you put into the system. So that's the case we would like to avoid. So with that said, in some of our recent work, we've been trying to do something which is a little different than what's been done in the literature before. Is if I take my motor input to the system, can I add a noise or energy in a certain bandwidth for a period of time to bounce my system from one orbit to another orbit? So what you see out here is the result of that. So basically, I have forward whirling in one direction with noise being added. This could come to drill bit rock interactions, or from your drive torque, I bounce out to another motion. Of course, in practice, this is not a situation we'd like to have. But again, this just shows the viability of using noise as a mechanism to control your dynamics of the system. This is something which is predictable. We can get your equations of motion, and you can also include your noise term in your motor input and go through and do a Galerkin projection to obtain the lower order system and play with that. And if you do that, again, these things are predictable. You get pretty much what you see in the experiments, that you're pretty much in one state of motion with noise included. You jump to another state of motion, and then noise is turned off, and you stay in that particular state of motion. So this area is relatively new. The question of using noise to move things around in dynamics is an area of research that people are looking at a variety of systems. But again, from a different standpoint, if you use the frequency domain, you're pretty much moving the system from one response branch to another response branch. So with that, you can also do it for a different case. So I'd like to come to a close. So what you saw today was pretty much three different aspects. One is where we used reduced order models to focus on the state-dependent delay and show how the penetration speed is something to capture that effect. You need to take the state-dependent delay into account. And the bifurcation analysis that we showed to you today also shows that damping can play an important role in determining what type of instability one has. The experiments, the lab scale experiments are quite useful to understand phenomena, in this case whirling in particular. The high dimensional models are valuable to understand both the complex nature, like the strain wave propagation, as well as stick slip motions and bit bounce motions, and how those come into play. Noise, as well as secondary frequency inputs, may be useful. Apart from that, although I didn't show the results today, in other experiments we tried to use high frequency inputs to control these motions. They seem promising as well. So in ongoing work with Qatar University, we supported the Qatar Foundation. So what you see in this rendition is a backward whirling motion. Without drill mud included, with drill mud, you could control those motions as well to stabilize it at a certain location. And if this motion were to continue, the motions do become violent. The drill string actually jumps out of the borehole itself in that particular case. So that's pretty much where we are at this stage. So thank you for your attention. I'll be glad to answer any questions that you might have. Thank you.
So, question time. Maybe if I can start.
Sure.
So you mentioned the whirling, and I'm assuming that the whirling has nothing to do with the bit-rock interaction.
No.
It is a weight imbalance.
Right. The whirling in this case is purely due to contact interactions with the borehole. Nothing to do with the cutting action. But in the studies that we did before with the full model, we do see whirling in that case as well. So in that case, the whirling is influenced by the bit-rock interactions too. But in the experiments that we showed today, it's purely the contact with the outer shell.
Yeah, because I mean, there's a lot of evidence that in the field that it's either whirling or stick slip. So this belief that both could be initiated by what's happening, the regenerative effect.
Yes, absolutely, yeah.
Questions? If not, I will continue to ask.
Yes.
I'm perplexed with your adding noise, and all of a sudden you jump from one stable state to another stable state.
Yeah.
Can you drive between those two? Is there a way that you can control between the two? Why is it that just all of a sudden going crazy and adding noise allows you to jump between states, but you can't figure out a method of doing it consciously?
Yeah, so I think that goes back to what I had in one of my earlier slides. The response depends on the initial conditions. So pretty much when I add noise, what I'm doing is I'm moving it from a domain of attraction of one response state to another response state. That's pretty much what I'm doing with the noise. I'm pushing the trajectory from one domain where I would be, where everything would take me to this smaller motion, to another state where I can push to other motions. So all the noise is doing is providing me an escape to go to that state. That's all it's doing. I think that is, in a nonlinear system, that's something one could expect.
Yeah.
Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah. Yeah.
I'm not sure if my observation is correct, but nonlinearity in your system only come from the bit itself, because the string is linear, it looks like, right?
String is linear, you're right. All the nonlinearities in our case come from the bit-rock interactions, and in the later case, also from the contact interactions with outer shell. So suffice to say, everything that I have is through contact interactions, contact and cutting interactions.
We discussed that this morning, but one of the most fascinating aspects I find is this standing wave that you're observing, and which means that if you are discretizing by a set of oscillators, they're all synchronized. Do you have any kind of insight about why that is happening? Because it is kind of related to this regenerative effect, and anything that you could tell us about why the physics behind this?
Yeah, I think, so if I were to think of the whole system as a set of coupled oscillators, so it's known in coupled oscillators, even in linear systems, that if I were to excite the system at certain locations, a certain set of oscillators don't move. The energy is localized in another set of oscillators. So I think by extension, in the drill string case, the forcing that we see is coming from on the top. RPM is one type of forcing, and then at the bottom. And then you have the gravity load that's distributed throughout the system. Those are the three primary sources of forcing for you. So it's just the manner in which the loading is distributed allows you that initial states or the modes that can get excited so the energy is localized in certain sets of oscillators. I think that's the hypothesis I can think of.
Mm-hmm. Any other questions? Yes, Henrik.
In a long string, I would think that the axial forces should be significant in the string.
Yes.
Those are built into the stiffness matrix?
Yes. Yeah. Yes. So I think going back to your earlier question that you raised, if I may go back to it. So on the drill string that we had, it was all not curved. So if I did take curved drill strings into account, then geometric nonlinearities do come into play. Like directional drilling is an example where that type of curvature could produce those nonlinear terms for you.
So if there are no more questions, then I will ask you to join me to thank the speaker.
Thank you.